revisit some of the results from your last course, which may be useful. Now, generally what we assume is L theta A is convex in A for every theta belonging to capital theta. So to get a feel of that, let us look at how should the loss function should be. So here it is the true value of mu theta. Mu theta is the true value. So your loss function, if theta is the true value, mu theta is the true value of the parameter which you want to estimate. So your loss should be 0 if my A is same as mu theta, or if my A is in the neighborhood of mu theta, my loss would be very small. And at mu theta, my loss would be 0 at A is equal to mu theta. And as my xn is away from mu theta, that means I am making more errors. So my loss should increase. So it says that, it suggests that my loss function should be like this. Now these are called bowl-shaped loss function. So my loss should be same as this. When A is same as mu theta, this value is 0. As my xn moves away, so this is 0 actually. So let me make a graph much clear. So I put my xn on the x-axis and L theta A over here. I am interested in estimating mu theta. So if I estimate my xn is same as mu theta, which is the true value, my loss would be 0. As my xn is away from mu theta, my loss would increase. So this would be like this. So I would prefer a loss function of this type. Now this loss function is called bowl-shaped. What is the bowl-shaped loss function? It is decreasing before mu theta and increasing after mu theta as a function of A. So in general, one may consider loss function L theta A such that for every theta belonging to capital theta, L theta A is a convex function. Note that a bowl-shaped function is always a convex function. So L theta A is a convex function of A. So that is why these convex loss functions play a very important role in parametric estimation. Before I go for a convex function, what is the definition of a convex function? First, let us see what is the definition of a convex function, which is defined on a real line. So suppose h is a function from D to R. D is an interval. So convex function says that f of alpha x plus 1 minus alpha y is less than or equal to alpha times fx plus 1 minus alpha times fy for every x and y in D and alpha belonging to 0 and 1. So any function f which satisfies this property is called a convex function. So let's try to see how does a convex function looks like geometrically. So note that if x and y are points over here, alpha is 0 and 1, so alpha x plus 1 minus alpha y is a mean of x and y, so it would be somewhere in between. So it says the value of f at this point should be less than or equal to value of chord joining fx and fy. So these are like a line joining fx and fy, which would be a chord in that curve. So it says your curve should be like this. So this could be f of alpha x plus 1 minus alpha y, and all these points are alpha times fx plus 1 minus alpha fy, because fx is over here, fy is over here. So alpha fx plus 1 minus alpha y would be points lying between this and this. So what it says is this point should always be less than or equal to this point. Or in other words, value of the function at a point should be less than or equal to chord joining the 2 points. Or in other words, tangent at this point should be less than or equal to, the tangent always lies below the curve. So this would be a tangent to the curve passing through f alpha x plus 1 minus alpha y should always be below the curve. Now, I will not prove those results, but it is known that convex function is always continuous. It is always differentiable almost everywhere. What it means is the set where it is not differentiable does not contain any interval. Now, if f is differentiable, then f is convex if and only if f prime is increasing. If f is twice differentiable, then f is convex if and only if f double prime is always greater than or equal to 0. So these are some of the properties of a convex function in R. One can define convex function in Rn. So what one can do is one can say that I have a function g h from D to R, where D is a convex set now, I say. Now note that why I require D to be an interval, because I want that if x and y are in interval, then for every alpha between 0 to 1, alpha x plus 1 minus alpha y should also be between 0 and 1. Or in other words, if the 2 points are in the set D, any line segment joining between them should be in that set D. So that means if x and y are in D, alpha x plus 1 minus alpha y should also be in D. Or in other words, if 2 points are in D, any line segment joining between them should be there. Those kind of sets in R1 are nothing but intervals, and that is why I had taken to be interval. Now when I take D to be a subset of Rn, n-dimensional Euclidean space, then my D has to be a convex set of Rn. So D is convex set in Rn. What does that mean? That means if I take 2 vector points x and y in Rn, I consider line segment joining them, which would be nothing but alpha x plus 1 minus alpha y. Now here alpha times x means alpha is multiplied to each component of x. That means alpha x1 plus alpha x2, alpha x1, alpha x2, alpha xn. So if x and y are in D, then alpha x plus 1 minus alpha y should be in D. And this should hold. Now again, it has same kind of a property, except that this property says the Hessian matrix H is non-negative definite, and ND, non-negative definite. This is equivalent to saying that f is convex. So this is the definition of a convex function in R. Of course, you know from your last course about the Jensen's inequality, which is one of the very important inequality in probability and statistics. What it says is if you have a function h from Rn to R is convex, then expected value of h of x would always be greater than equal to h times expected value of x. So what it says is, provided expectations exist, what it says is if you take the average of h of x, that would always be greater than equal to if you apply h on the averages of x's. So averages of hx would always be greater than equal to h of averages of x's, it says. Now this is one of the very important inequalities, and this inequality is used to reduce the class of estimators under consideration, which again you must have done in your last course. So let me just briefly touch upon those results. So note that why we are going to use these results, because when we are talking about a risk function, there are two randomization involved. One randomization with respect to yx, one randomization with respect to x. And you are talking about expected average loss. So that means possibly if I, rather than considering yx, if I consider their averages of yx, that might give me a reasonable estimator, especially if h is, especially my loss function is convex. So let's try to see that. So the first result which we are doing over here is, suppose my xn space is same as parametric space, which is same as whole of Rk. Tx is a sufficient statistic for theta. Delta naught is a given estimator. For mu of theta. It could be randomized estimator or non-randomized, any of that. Randomized or non-randomized. Using this delta naught, and suppose corresponding random variable is y naught x. Because if you have a delta, which is a probability measure, corresponding to a probability measure, you will have a distribution, you will have a random variable y naught x. Now in case of non-randomized estimator, y naught x would be taking only one value with probability 1, depending on x. And in case of randomized estimator, y naught x would have a non-degenerate probability distribution. So what I define is, I define delta 1 A delta 1 given x by, which in fact I can write down, it only depends on Tx as expected value of so I define delta 1 A given x as expected value of A given Tx. So what it does is, it takes average with respect to conditional distribution of x given Tx. Or in other words, if I take corresponding random variable as y1x, which is basically y1, it will only depend on Tx. This is nothing but expected value of y naught x given Tx. So whatever was the random variable corresponding to the given estimated delta naught, it says you take average of that, and the average is taken with respect to conditional distribution of x given Tx. I get a new estimator delta 1, and this delta 1 basically depends only on Tx. Then what it says is, you try to find an estimator. So basically what you have is delta 1 A given t is nothing but expected value of delta naught A given x, given that Tx equal to t. Right? So this expectation is with respect to conditional distribution of x, given that Tx equal to t. Then R delta naught theta is same as R delta 1 theta for everything. So what this suggests? Delta naught was any estimator which was given to be depending on x. Using delta naught, I can get another estimator delta 1. And how do I get delta 1? I just take the average of corresponding random variable y naught x corresponding to delta naught with respect to conditional distribution of x given Tx. So I do a randomization with respect to distribution of x given Tx. Now the only issue could be when you take the expectation, your expectation may depend on unknown parameters. So you have to make sure that this is a proper estimator. That means it only depends on x and nothing else, because it may also depend on theta when you are taking expected value. But since Tx is a sufficient statistic, distribution of x given Tx does not depend on theta. So when you are taking expectation with respect to a distribution whose distribution does not depend on theta by virtue of t being sufficient, or equivalently distribution of x given Tx being independent of theta. So in that sense, delta 1A given x does not depend on theta, so it is a proper estimator. It only depends on the observation x. And in fact, it depends on the observation x only through the sufficient statistic Tx. And then risk of delta 1 is same as delta naught. So an easy consequence of this is saying that given any estimator delta naught which depends on observation, I can find an estimator which depends on a sufficient statistic. So that estimator is delta 1, whose risk is same as the risk of the original estimator delta naught. So what it suggests is you can restrict to only those estimators which depends on observations only through sufficient statistic. So if sufficient statistic is not unique, so I would certainly look for a statistic which is minimal sufficient. So what this suggests is enough to restrict to estimators that depend on observation only through minimal sufficient statistic. So let me just again summarize a bit. It says if you are given any estimator delta naught, this could be randomized estimator, this could be non-randomized estimator. It says if you are given an estimator delta naught, you take its expected value with respect to conditional distribution of x given Tx. So that is what it says y1x, I take a new random variable whose distribution is which is same as expected value y naught x given Tx. So this y1x only depends on Tx. And corresponding probability measure I am saying is delta 1A given x. Then I see the two estimators have the same risk. Or in other words, given any estimator delta naught, randomized or non-randomized, I can get an estimator delta 1 which depends only on the sufficient statistic and whose risk is same as that of delta naught. Or in other words, it is enough to restrict oneself to class of estimator which depend on observations only through sufficient statistic. If that is the case, then certainly I would like to restrict myself to the estimator which depends on the minimal sufficient statistic, because that is the minimal sufficient statistic gives you the maximum reduction of the data. So what it suggests is this remark which says it is enough to restrict to estimators that depend on observations only through minimal sufficient statistic. Now note that this delta 1 can be randomized even if delta naught was non-randomized. So, I leave that as an exercise. What happens to delta 1 if my delta naught was non-randomized? Can I say that my delta 1 would also be non-randomized? Now, then let me do this another result. Now, this you must have done in your earlier course. If not, just try to do it. Basically, what it is, the fact which is used over here is expectation is same as expectation of a conditional expectation. So, when you are taking expectation with respect to x, you write down that as expected value of x and expected value of x given tx, and the things would follow. Just try to write it down. So, now let us try to see this result. Suppose A is a subset of Rk, theta belongs to capital theta, my loss function L theta A is convex in A for every theta belonging to capital theta. Delta naught is given randomized estimator. I define delta 1 and suppose the corresponding random variable is y naught x. I define delta 1 x as corresponding random variable y 1 x, which is nothing but expected value of y naught x. So, note that my y 1 x is expected value of y naught x. So, that means for given x, so let me write down y 1 small x, observed value of x. This is a mean of y naught x. So, it says after x has been observed, whatever randomization was done through y naught x, I do not consider that, I only take the mean value of that. So, in that sense, this is a non-randomized estimator. Why? Because it just takes the mean of y naught x. Mean of y naught x, there is no randomization involved, there is only x over there. So, it will only depend on x. So, here y 1 x takes value, whatever this value is, you may call that as Ax with probability 1. There is no further randomization involved over here. Then L star theta delta 1 x would always be less than or equal to L star theta delta naught x. In fact, in this case, this quantity, because it is no randomization is involved at the second stage, this would be nothing but L star theta and this y 1 x, because that is the xn you will take. So, what it says? Says that means if your loss function is convex, then given any randomized estimator delta naught, you can get a non-randomized estimator delta 1 x whose risk is smaller than that of a randomized estimator. And how do you get this delta 1 x? It's very simple. It says don't go for a randomization second stage, whatever randomization random variable was there, take its mean as your xn immediately after observing x. So, for example, in the case of x1, x2, xn, IID normal theta 1, and suppose my delta naught was corresponding random variable was yx, which is normal x bar 1. So what was the randomized estimator over here? It says after observations x1, x2, xn have been taken, take their sample mean, and then generate one observation from normal, having that sample mean as a mean and variance 1, and take that as a estimator by x. So what it says? What would be the delta 1x in this case? In this case, says delta 1x is nothing but a mean of this distribution. You don't take that as a estimator. Don't go for a second stage randomization, which is saying that take one observation from normal x bar 1. It says just take the mean of that itself. So delta 1x is nothing but y1x, which is expected. So these are y0 x, expected value of y0 x, and expected value of y0 x is nothing but x bar. So here y1x directly depends on x bar. It is a random variable which is degenerated at x bar for a given x. So what it suggests? This says that it is enough to consider non-randomized estimators if your loss function is convex. Non-randomized. If loss function is convex. Convex in A. Why? Because the risk of the new estimator which you get delta 1x, which is a non-randomized estimator, not risk, the loss is less than or equal to this for every theta, so risk would further be less because that would be expected value of that. Now, finally, let me just do the Rao-Blackwell theorem, which you again did in your last course. So suppose my theta is same as A is same as Rk. For every theta belonging to capital theta, L theta A is convex. Rk. Tx is sufficient. Delta naught given randomized estimator. I define delta 1 Tx as expected value of delta naught x given Tx. So that means you take expected value of delta naught with respect to conditional distribution of x given Tx. Now note that Tx is sufficient, so conditional distribution of x given Tx does not depend on theta. So that means this quantity only depends on this whatever is given to you, which is Tx, not on theta. So it is a proper estimator. Then R delta 1 theta will always be less than or equal to R delta naught theta for every theta. With a strict inequality if your loss function is strictly convex, or when delta naught x is not equal to delta 1 t with probability 1. So what this suggests, if you combine the proof, if one has to look at it, just follows from the Jensen's inequality. So I leave it because you must have done it in the last course. I'm not doing it over here. But it's just an immediate consequence of your Jensen's inequality. So what these two results suggest is, if L theta A is convex in A for every theta, then first result says it is enough to consider only non-randomized decision rules. because given any randomized estimator, you can find a non-randomized estimator whose risk is smaller than the given delta naught. This again follows by the Jensen's inequality, because this y1x is nothing but an average of y0x. So it's just simple application of it. So enough to consider this result ensures that if your loss function is convex, you should only consider non-randomized estimators. What does this result ensures? That if your loss function is convex, then given any randomized estimator, you can find a randomized estimator based on sufficient statistic such that the risk of the estimator, non-randomized estimator, which depends on the sufficient statistic, is small. So if you combine the two result, it says enough to consider estimators that are non-randomized and depend on minimal sufficient Why minimal sufficient? Because minimal sufficient statistics are the one which gives you the maximum reduction in data. So this was a brief discussion of essentially what you did in the last course. So from the next module onwards, I'll start the actual content of this course. So the first topic which we are going to discuss in the next module is invariant estimation. Now, invariance is a principle which says that if you are dealing with a invariant, or if you are dealing with an estimation problem which has a structure which is invariant, then only certain kind of decision rules or certain kind of estimators should be used. Now, advantage of that is because invariance looks like a reasonable criteria, it helps me in reducing the class of estimators under consideration. Now, if it helps me reducing the class of estimators under consideration, it is possible that in this restricted class of estimators, I am able to find the best estimator. So that would be for the next module. That's all for this module. Thank you very much.